We've all seen the output of cloud-based UI generation, probabilistic layouts that drift, morph, and shift unpredictably across the screen. The industry calls this AI slop. These interfaces are ported straight from cloud-native design systems. They rely heavily on deeply nested HTML containers and resource-intensive rendering effects, like glassmorphism, to maintain a modern aesthetic. That design philosophy completely ignores the physical reality of local hardware. When you run an agentic AI directly on an edge device, like an Android terminal or an NVIDIA Jetson, you immediately hit severe RAM constraints. The problem compounds at the data layer. Standard architectures pass state using UTF-8 text-based JSON strings. Every time the UI updates, the edge device's CPU burns cycles reading text and decoding it into memory objects. Combine a probabilistic, drifting design language with a bloated text-parsing data structure, and you starve the local hardware. The system bottlenecks, runs out of memory, and crashes. To survive on the edge, the entire stack has to be rewritten. The solution requires a fully deterministic ecosystem where the user interface and the back-end data are unified into a single relational matrix. This architecture is orchestrated through a specific development environment, the BEJSON plus BEHTML dual IDE. The visual result is immediately striking. It enforces a strict brutalist layout, completely devoid of gradients, drop shadows, or rounded corners. Look closely at this dashboard layout. The high-contrast palette of white, black, and red serves a specific engineering purpose, maximizing legibility while minimizing rendering overhead. The stark, cubic interface you see on screen is the direct visual expression of the bare metal, binary-encoded database operating underneath it. To understand how this matrix functions, we will examine this diagram breaking the interface apart. The 2D plane tilts back, splitting into 3 distinct structural layers. We start by examining the top visual surface. This top layer runs on the Brutalist Style System, or BCAS. Its core principle is flattened depth. Instead of stacking elements inside one another, the interface breaks apart into flat, non-overlapping geometric blocks, prioritizing stark dividers and whitespace. Infinitely nesting HTML containers are actively banned. Every element must snap to a single flat horizontal plane to guarantee deterministic rendering. At the code level, this unnested structure is enforced using a strict block element modifier, or BEM, naming convention. It prevents developers from accidentally introducing nested complexity. Flattened depth serves a dual purpose. For the human operator, it creates high-contrast, immediate legibility. For the local AI agent, it creates a perfectly predictable environment to parse and interact with. By forcing all components onto a single, unnested plane, the system mathematically eliminates the cascading layout drift that defines AI slop. Moving one level down in our teardown, we find the mechanism that controls that exact placement, the BEHTML spatial grid. This grid diagram illustrates the law of positional integrity. Every component functions as a physical object mapped directly to absolute X and Y coordinates in the database. The measurement brackets lock in to reveal a strict pixel rhythm constraint. Every element's height must be an exact integer multiple of 32 pixels. If elements need to overlap, the system uses z-index depth layering, allowing components to stack upward without violating their assigned positions on the two-dimensional grid. When a layout violation occurs, like a component trying to expand to a non-grid-aligned height, the system's internal anti-drift auditor immediately catches the math error. It flags a matrixed shatter, or error 308, and violently snaps the component back onto the approved grid lines. At this level, the user interface ceases to be a traditional web document. It operates entirely as a mathematically bound spatial database. At the very bottom of the teardown lies the memory foundation, the BJSON 104DB binary buffer. Standard AI architectures rely on network transport protocols, like HTTP2, to send data back and forth. This environment abandons network calls entirely in favor of high-speed local inter-process communication. As this diagram shows, sending UTF-8 text streams creates a massive CPU bottleneck. The solution is binary encoded JSON. Data is packaged as a continuous binary stream, with explicit integer lengths mapping out the exact byte segments. By encoding field lengths and data types as explicit byte offsets, the database creates a physical map of the information. This enables zero-copy deserialization.
The local agent's reader head can jump instantly to a specific byte offset to read a grid coordinate, completely bypassing the need to load the rest of the file into RAM. Eliminating text parsing is the only architectural way a local coordinator can traverse a complex interface grid without crippling a low RAM edge device. This binary efficiency becomes crucial when handling media. Cloud AI systems are forced to encode raw video frames or depth maps into base64 strings to send them over standard network APIs. Look at this diagram detailing the conversion process. Transforming simple visual data into text characters introduces massive memory bloat and severe latency. BJSON bypasses text encoding entirely. It supports native bin data byte arrays, instantly collapsing the bloated text block back into a compact, tightly packed array of binary data. Because of this native binary support, local agents can take raw camera streams and hand them directly into the UI's memory without running any conversion protocols. Packaging media this way drastically cuts RAM usage and prevents latency. It gives edge hardware the bandwidth required to run real-time multimodal AI operations locally. Beyond the database architecture, the operating environment itself has to be engineered for survival. The physical limits of the hardware dictate every operational rule. RAM must be violently conserved at all times. This process diagram illustrates the system's modular launcher script. Its primary directive is absolute resource control. When a new application node attempts to connect, all existing background services turn red and instantly terminate. The system ruthlessly purges active background processes to grant maximum memory and CPU resources to the single requested application. True edge architecture requires abandoning traditional multitasking in favor of focused, single-process efficiency. Reversing the teardown, we can stack the binary buffer, the spatial grid, and the visual surface back together. The raw binary buffer aligns perfectly with the spatial grid. Every single byte mapped in the database corresponds to a physical coordinate on the screen. When combined, that mathematically perfect grid renders directly into the stark, cubic red and black surface of the interface. Look at the fully assembled dashboard here. This brutalist aesthetic functions as the literal, physical expression of bare metal efficiency. Treating the user interface and the underlying data as a single deterministic relational matrix ensures layout stability and memory optimization. It provides the definitive blueprint for scaling agentic AI directly onto constrained local hardware.